Yo, what's up, everybody? Welcome back. Today we are working on writing a GIF viewer. GIF viewer, GIF viewer. I don't care. Some people do, so I'll just say them both so everyone gets pissed off. But context is my monitor broke. And I used to hold chat on my second monitor. But now I do not. I hide it under my camera here. But this like the Twitch chat client is like not really built to be this small, and so I actually have to like this bar is actually kind of annoying. I tried to remove this, but I like every time I launch chat, I inspect element and remove a bunch of stuff so that like I can actually see what's like a little bit in there. And so we're like, fine, we'll finally write a Twitch chat client. And one of the things that a Twitch chat does is they will send emotes, and we need to be able to display them. There's a lot of things that we don't display, like UTF-8 text correctly, for example. But, you know, we should be able to show emotes. And so somebody sent one earlier. We opened it. It was this. We have some animated GIF. And if we want to display it, because no dependencies are allowed, we have to parse it. So the plan for today is to try to figure out what the hell this thing is. And if we can render it, that would be kind of cool. So I don't really know what's in there. So really it's going to depend, like what we do depends on what we find. But I think, you know, first up, maybe we just hex dump this thing, right? Maybe we just hex dump this thing. And let's take a peek. Looks like we got some sort of GIF header. Stop saying GIF/GIF, just say GIF, please. Thank you. And I have there is like nothing in here that is telling me anything, right? It's a bunch of data. What a shocker. The only thing that we can recognize is this GIF 89A. Be good now, chat message might appear on screen. No, not anymore. We closed it. You're good. You can say whatever heinous shit you want. Streamer can't read GIF hex. Yeah, sorry, my bad. GIF file format. Wikipedia? They usually have like an overview in here. File format. Here we go. Let's take a little peek. Should we trust Wikipedia or should we find some spec? Wikipedia. let's look at something that is not reliable. I shouldn't say Wikipedia is not reliable. It's like pretty good for a lot of stuff. It's way less reliable than a spec. But we're fine. Okay, so conceptually we describe a fixed size area, the logical screen populated with 0 or more images. Okay, many GIF files have a single image that fills the entire logical screen. Others divide the logical screen into separate sub-images. The images may also function as an animation in an animated GIF file, but these need not fill the entire logical screen. Okay. GIF files start with a fixed length header, one of these, given the version. So we have the second one. Followed by a fixed length logical screen descriptor, giving the pixel dimensions and other characteristics of the logical screen. Okay, so that's like 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So here, I would assume that it's like, this is probably the size, width by height in 16-bit, right? Because I think that our file is 28 by 28. 1C sounds a lot like 28, right? That's 16 plus 12. I think A is 10, 11, 12. So yeah, 28 by 28. So here's the width and the height of the logical screen. The screen descriptor may also specify the presence and size of a global color table, which follows next if present. Thereafter, the file is divided into segments of following types, each introduced by a 1-byte sentinel. So an image is a comma, an extension block is an exclamation point, and the trailer is a semicolon. So we should see commas in here somewhere for images. I don't see commas, exclamation points, or semicolons in here. But maybe this is like the table still, right? Maybe this 87 says like we have 87 bytes of colors, right? So maybe like this is all color info, and then can we look for we see exclamation points here and here. Okay, and then a comma here. So this is an image starting from here probably, and then we should see that this image goes until some semicolon, and then probably we have like a sequence of these images or something. There's a comma on line 3. Did I miss it? Oh yeah, right here. Good eye. And then can we look for like semicolons? So here, semicolon, but not followed by a comma, which is interesting, right? It's kind of interesting. Okay. An image starts with a fixed length image descriptor, which may specify the present size. Oh, so maybe like some of these semicolons and commas might be like within some like sized block or something. Okay, here we go. There's a specification. Let's just look at that. Let's look at that. Boring, boring, boring. Here we go. No, wait, hold on. Let's look at the chapters. Where does it talk about like the fucking overall? The encoder, the decoder, a compliance, about blocks extension of the scope, probably. Compliant, okay. Here we go. Data subblocks are units containing data. They do not have a label. These blocks are processed in the context of a control. Blocks, however, blah, blah, blah. Where's, like, the fucking, like, start? Where's, like, the like, header? Oh, here we go, header. Wait, here we go. This is what I'm looking for. Header. The header identifies GIF data stream in context. The signature field marks the beginning of the data stream, and the version field identifies the set of capabilities required of a decoder to fully process the data stream. This block is required. Exactly one header must be present per data stream. Required version, not applicable. The block is not subject to a version number. The block must appear at the beginning of every data stream. Okay, beautiful. So we have signature 3 bytes, version 3 bytes. So we have GIF 89A. So 89A is, I see. So we've got the version that was introduced in 1987 and the version that was introduced in 1989. And then I assume that we just keep scrolling down and they'll keep telling us more, right? That sounds right. And it looks like our block diagrams are bits, right? So they have each horizontal here is 1 byte and each vertical here is 1 bit. We're going to have to at some point probably look at that. He keeps saying GIF, not GIF. GIF, not GIF. Whatever. Yeah. I'm trying to alternate, but I might be forgetting. Okay. Let's do this. Let's open a GIF. So we have const stud is import stud. And I guess here we're kind of actually trying to parse something now. So where are we in terms of time? 7 minutes. Oh, 7:51. First code. I guess we're trying to like parse overall structure. And then we'll kind of look at individual details later. Okay, so we have some file in here that is some emote. And let's get a reader for this thing. Maybe, actually, do we just want to read this into a block of bytes? That might be easier. Stud fs. Is there like read file alloc? There is. There's also just read file into some buffer. Let's do that. Right, so we have some buff. GIF data buff. And we have like 8 megs of stack space. So certainly like 4 is fine to use here. And let's do this. So some emote into this buffer. And then this should give us data here. And we should see, I don't know. Maybe we want a reader? We might. I don't know. I feel like that's how, like, you do most stuff in Zig data parsing, so why not? And we want to read header, so where was our stuff? Where was our thing? Okay. I don't know. Maybe we're starting with like a parser. I guess since we don't know what we're doing yet, just like doing it all inline makes sense. Once we find the full structure, then we can kind of find an abstraction that works, probably. So we know that we want like 6 bytes, right? And we are expecting the, I guess it's like 3 and 3, right? So it's like sig and version, right? And so here we're expecting the signature to equal GIF, return error, not GIF, or invalid signature, I guess. And then we're expecting the version to be 89A, because surely nobody's using the version from 1987. Surely. Right? Surely. All right. He's mad because we have to write try on these. Okay. And we're chilling. So if we're like, hey, could you be 87? He's going to get mad at us. Beautiful. So we have successfully parsed the first 6 bytes. Let's fucking go. Logical screen descriptor. So the logical screen descriptor contains the parameters necessary to define the area of the display device within which the images will be rendered. The coordinates in this block are given with respect to the top left corner of the virtual screen. They do not necessarily refer to the absolute coordinates of the display device. Okay. This implies that they could refer to window coordinates in a window-based environment. Okay, right, because this is written in fucking 1989, right? So windows were like a novel concept. Right. So this block is required. Exactly one logical screen descriptor must be present per data stream. All right. So we have unsigned, which I assume there are 2 byte values, right? It must be. Then we have some packed fields, background color index, pixel aspect ratio. That's crazy. Okay. So we have is it big or little endian? It looked little from what we saw in the hex dump. Can we look at like the unsigned type? Does it explain what this means anywhere? Not really, huh? Well, whatever. We'll do this. So what is it? It's width. So this is a take int u16, and we think it's little, and height, right? We have this. Boom. Hello. Okay, width. Height. Easy. He's mad because the 2 bytes is implied, so true. What? Wait, what's he pissed about? Invalid format string D. Am I stupid? Is D not... Oh, I see. Try. Yep, you're right. Thank you. 28 by 28. So that's good. That is the size of our thing. So then we have packed info is something that we don't know yet. But we can do that. Then we have background color indexed. And pixel aspect ratio. Okay. So the packed field is global color table flag, color resolution, sort flag, size of color table. And then it looks like we have, this is the top bit. Then this is the next ones. So this is top to high, most significant to least significant, which we can represent with a zig packed struct, I think. Which I can't remember which way they go. One sec. Hello, DuckDuckGo, could you please load a web page? Thank you. Thank you. Packed struct. So is it most to least or least to most significant? A range from least to most significant. So we invert this for our thing. Packed info. So this is color table size, which is how many bits did he say? 3. He's got sort. He's got res, color res, as U3, and then he's got color table present or something like this. Can we do bools instead of U1s? And so then can we do take struct here instead with pack info, and it doesn't matter, but we can write little Indian here. And then can we print all this stuff? I don't know. Okay. Background color, pixel aspect. Color, boom, boom, boom. That should be obvious. Why is he mad? Oh, because take byte doesn't have a number, because of course, it's 1 byte. Can we new line after these? Thank you very much, kind sir. Okay, so color table size 7, sort false, color resolution 0, color table present true. Okay, so that seems consistent. But let's see. So this defines what all this stuff means. Flag indicating the presence of a global color table. If the flag is set, the global color table will immediately follow the logical stream descriptor. This flag also selects the interpretation of the background color index. If the flag is set, the value of the background color index should be used as the table index of the background color. Otherwise, what? 0, no global. The background color index is meaningless. I see. So if there is a table, then it uses them. Got it. Got it. Okay. So if we have the color table, we should be able to take the next, like, however many bytes, right? So this is this many bytes of size, right? The CT size. The color table will immediately follow that. Does it tell us? Like, I'm assuming that the size feels obvious to me, but we should. I'm just trying to like confirm that that is what we're trying to see here. Oh my god, that's annoying. Global color. Okay. I'm assuming it's in bytes. I'm assuming. This block contains a color table, which is a sequence of bytes representing red, green, blue color triplets. The color table is used by images without a local color table and by plain text extensions. Its presence is marked by this. If present, it immediately follows the logical screen descriptor and contains a number of bytes equal to, here we go, 3 times 2 to the power of size of global color table plus 1. Okay, so see, like, CT size bytes is 3 times 2 to the power of CT size plus 1. So we should be able to take this thing, right? Color table is this thing. Something like that. And can we print this thing? Okay. Fuck. Int cast to what? What is the size? U8 or so. I don't know. I guess it's this, right? So U size? Maybe like this? Okay, integer overflow here. Because CT size is a U3, so this we probably want as like a U6 or something. I don't remember how many bits are allowed to be shifted into U size. Probably U8, right? Or U7, one of those. There we go. Okay, so that looks like a pretty sane color table, right? We see some form of like monotonically increasing values ish, which is like what would make sense if you were generating one. I mean, it's not perfectly monotonically increasing, but these are triplets, right? So can we do something like try to format them as 3s? So var I is a U size while I is less than color table len or something. we do I plus equals 3, and then can we print this thing as a 3? Like this. I color table I times 3 color table I times 3 plus 1 and color table. I guess we can do this. We can go from I times 3 to I times 3, like, I guess we do a little 0 to 3 like this. There we go. Too few arguments. Less than. Why am I stupid? Am I crazy? So, oh, I'm an idiot. Needs a new line. True. Okay, there we go. So that seems kind of sane, right? We're seeing like kind of RGB values that are kind of like overall increasing or something. Seems reasonable. Seems reasonable. So after the global color table, we should have an image descriptor, right? Or we should start seeing, I guess, like the next byte of this thing. So can we say like, can we like write down what the next byte is? Next byte is this. And can we just do like try our take byte or something? Because we should see an exclamation point. That's good. Okay, so now we are in the like part where they were talking about on Wikipedia, like the exclamation point or the comma recommend like explaining blocks, right? So we're in an extension block now, and then so can we look at extension block? Okay. An application extension contains an application-specific information. It conforms with the extension block syntax as described below, and its block label is 0xFF. So we should see 1, 2, 3, and then we just skip, right? I assume that the block size here is number of bytes in this extension block, following the block size fields up to but not including the beginning of the application data. This field contains a fixed value 11. Oh, I see. So it's to jump over this stuff here. Then how do I know how big the application data is? Maybe the application data is just not allowed to contain a semicolon. You just have to scan forward till you find one. I think Firefox gives that information in the network tab. You're not going to trick me into revealing my cookies again. It was only one time. One time. Data subblocks. Maybe we're supposed to look at that. Yeah, so page 5 has data subblocks here. Our units contain data. They do not have a label. These blocks are processed in the context of the control blocks. Whenever data blocks are specified in the format, the first byte of the data block indicates the number of bytes, the number of data bytes to follow. A data subblock can contain up to 0 to 255 data bytes. The size of the block does not account for the size byte itself. Therefore, an empty subblock whose size field contains 0, 0. Okay, got it. So we want to parse out the like extension block stuff. So this is like a while loop now, right? While true, we like take one byte, and depending on the byte, we do something, right? So we'll say like, what is this next thing called? I can't remember. Block type or something? Maybe something like that? And we probably do like block type is an enum here who has one of exclamation point, semicolon, no, not semicolon. It's literally just these two, right? So we'll do like a block type string, and block type is string to enum of I guess we just do this. We can actually, we can get clever. This is stupid. We don't have to do this. It's 1 byte. The strength to enum trick is only required when you have strings. Switch on the block type. we can just write down this, right? I'm a fucking idiot. Okay, so we have this, and what was the other one? It was comma, right? And then else return error invalid block type. More metaprogramming, please. No. Well, unreachable here because we don't know what to do yet. Less real programming, only metaprogramming. So true. Okay, so if we see this thing, where do they talk about the extension block? This, right? So label is 1 byte. Then we have block size is supposed to be 11 is what they said, right? So we do like r take byte for the label. Then we have the block size. And this is supposed to be like 11, right? If block size is not equal to 11, return error invalid extension. So then we can just like take block size, okay, and then we're in the application point. So then we do while true, we try to read a data sub block. So it's like read sub block. And I guess we're just like discarding. So it's like try r take 1 sub size, and then we're doing like an r discard all of sub size or something, right? Something like that. And then if we see the block terminator, right? That's the problem. It's like I don't know. Block terminator. Like, what is this? All zeros. Ah, right. Okay. So, if sub size equals 0, this is take byte. We break. All right. Cool. Okay. We could probably print something interesting in here, right? Because we can at least see, I think there was like a name or something in here. Right, we saw app identifier in here. So maybe we print that. That's 1, 2, 3. This is 0 to 8. That's 8 bytes, right? 1, 2, 3, 4, 5, 6, 7, 8. I can count. Clonky! What's up? Welcome. Thanks for the sub. Okay, so instead of skipping the 11, we probably want to take the first 8. We just print it. We just print this. App stuff. Stud, debug, print. The app stuff. And we'll print as a string. Fuck it. 420 blaze it. Okay. Netscape 2.0, so that's good. And then we are seeing invalid extension at some point, which is probably bad. Right? We're seeing a block size that isn't 11. But I guess, like, maybe that's only for application extensions. Right? So maybe the label is important here. Maybe? I don't know, man. Don't fucking ask me. So yeah, if we see label 255, I think that lines up with this saying that the block label is 0xFF here. So what is going on here? So sometimes there's going to be 249, which is what? Can we print this as hex? So can we see like F9? Ah, here we go, baby. Here we go. So I assume that like these are all following some general format, right? So probably like all extension blocks have the block size here. But like, yeah. So probably each extension has like subdata. So we can probably parse them all the same. Right? So I think every extension will follow this format where we take the block size and then this is like the extension stuff, like extension header, I guess is what we can call this, and then it has subdata like this, right? Then eventually we're now getting to image data at 69, right? We're getting here. He's angry. So can we figure out what the fuck is image data now? Image descriptor here, right? Image descriptor at here. Each image in the data stream is composed of an image descriptor, an optional local color table, and the image data. Each image must fit within the boundaries of the logical screen as defined by the logical screen descriptor. I guess we're kind of parsed overall structure is probably okay. Well, I guess we need to get the size of this thing out first. But then we'll have to parse image data eventually. But for, I guess, to finish off this chapter, we have to get through to the end of the file. I guess that's kind of like the goal here. So, okay. Image descriptor contains the parameters necessary to process a table-based image. Coordinates given in this block refer to the coordinates within the logical screen and are given in pixels. This block is a graphic rendering block optionally preceded by one or more control blocks such as the graphic control extension and may optionally be followed by a local color table. The image descriptor is always followed by image data. So we start with the image separator, which is the fixed value 0x2c. I assume 0x2c is the comma. I assume comma 2c. Yeah, okay. So we are in the right spot. So this is kind of the header here for an image. Then where is the like image data part though? Right, like doesn't it need, maybe it's image width by height kind of lets you infer where it is? That seems kind of reasonable. So, because it's said in here, the block is a graphic rendering block optionally preceded by control blocks. Image descriptor is always followed by image data. So is image data another thing? It might be. Okay, let's just parse this stuff out first, and then figure out the rest after. All right. So we want. Can we comment all this? We want our take byte. This is this is a separator, so we've already found that. We have 2 bytes for left. Right? Like this, right? Or top. Then we have width and height. And then packed. So this is options, I guess we'll call it. And we're going to do a take struct again. That is image descriptor options or something. Absolutely disgusting. This slob is coding manually. Bro, open up a delicious Claude Code terminal. What is this in 2026? I honestly, it's so fucking stupid, I can't tell if you're joking. But like, I'm taking it as a joke so that I don't ban you immediately. But good one, I guess. Okay, so this thing is in reverse order of whatever the fuck they wrote. Local color table size. We got reserved. We got sort. We got interlace. We got local color table present. It looks like. It's not a joke. I open up OpenClaw and mog you with 16 agents at the same time. Okay, well, that's cool for you. You can just go fuck yourself. I'm not gonna I'm not going to justify myself to you. I have to not take the bait. But uh okay, how do I say this in a way that's like not like super mean? If I'm gonna ban you before you continue talking, because I don't want to talk to you, but I do want to talk to the other people who might hear that and think it's true. But like the AI code output is garbage, right? It's really bad. When I've tried it, I can't produce something that like resembles what I want. I think that you don't learn anything when you're doing that. I think the hard part of coding is not writing the code, right? It's figuring out what code you want to write. And so like if you're using these like fucking AI tools, you're like spending more time fighting with getting the AI to output the code that you wanted, which is like not even the hard part. The hard part is figuring out which code you want to begin with. So yeah, obviously no. I think that was satire. Well, if he doubles down and says that he's not joking, then like, he can get banned. I don't give a shit. Not even the AI enjoys or that's. I think they are some of them. I think they are. Okay. So what is in this thing? Can we print this? So we get our options, and then I think that there's some sort of image data block after, right? So there might be a local color table. So if there's a local color table, does it immediately jump after? Did it say something about that? Local color table. Immediately following. Okay, so if options local color table present, which I assume that we are going to have false actually. Because we have a global color table, so this thing probably isn't there, right? So can we like print out like just what we have here? Image block. So we have here, here, to here, and here. Left top to left plus image. I guess we'll just say image width by height, and then we don't have to do any math. Hebby, thank you for the raid. What's up, you guys? We are in the process of trying to write a GIF viewer or GIF viewer, whichever one makes you more mad is the one that I pick. And we are trying to do that because we are trying to write a Twitch chat client because my monitor broke and I need to like display chat. I don't like the fucking one that's in the browser because when you try to like shove it in the corner, there's a bunch of garbage in here that you don't want. I also already like deleted a bunch of HTML elements, but you still like don't get that much. So I want like, something that is better. And of course, we always do that shit ourselves, right? No dependencies allowed. And so if we want to show emotes in our Twitch chat client, then we need to be able to load emotes. So we're writing a little GIF viewer. That's what we're on today. That's what we're on. Okay, so this guy, local color table, if it's present, is its size, it's the same 3 times to the power of size plus 1. It's this shit again. But we're assuming this thing doesn't exist, right? So let's start there. Stood debug assert options local color table present is false. Quick, there it is. Get it before it goes away. Oh, the bop. Hell yeah. Is that the one? Open image in new tab. Hell yeah. Let's get this bad boy. Bop. All right. Hell yeah. Okay. So we're hoping to see an unreachable here at 115. Which means that this assert did pass, so we have no local color table to deal with. I'm all about doing these about chattering those guys. Yeah. Obviously. There's a real answer to this problem, but we're just, it's not really about that. Right? It's never about actually getting a thing that we want. It's always about the process of getting to the thing that we want poorly. It's fun. Yeah. Exactly. Exactly. Right? If you can't just say, I need a Twitch chat client, let me get one, right? It's let's make up a reason to write some code is like the real answer. Right? We're looking for reasons to explore concepts. Like, how the fuck do we decode a GIF? GIF. Okay, so after the local color table, I assume that table-based image data. Seek the image data for a table-based image. Well, what is a table-based image? It's if we have a global table or local table, right? Which means that, so if the local color table is not present, we use the global table if available. So we probably have to check. There's probably like a version that is not table based, right? So what happens if we do not have either? That's not clear. So for now, we will just write that we are asserting that the global table is present. So we have like packed info, color table present, right? Something like that. It's an image that you can move around. So not built in, i.e. not a counter-based image. I don't know what that means. I can't tell if you're trolling me or not, so I'm just gonna ignore you. The perfect solution. Okay. Table versus counter. Is there really counter? Are you fucking with me? Counter. I think this is a joke that I'm not getting. But I don't know. I'm sure a service union. Oh my fucking god. Oh my fucking god. So fucking stupid. Yeah, that's my bad. My bad. I should have caught that one. That is my type of joke. I just missed it. Yeah, of course. Yeah, I eat on the table or the counter. So this is a counter. Fuck. It's because counters are like in programming land. Like the counter is so embedded in my brain as like an index, right? So it's like I completely missed that one. That was a good one. Good one. You got me. Okay. Consists of a sequence of subblocks. So we already know how to parse a subblock. We have a size followed by data. It looks like it is compressed with LZW, which I don't really know what that is yet. Consists of a sequence of subblocks of size at most 255 bytes each, containing an index into an active color table for each pixel of the image. Pixel indices are in the order of left to right from top to bottom. Each index must be within the range of the size of the active color table. Right, so if we see anything that's like, we have a table somewhere and we're like indexing to that color palette, easy peasy. Sequence of indices is encoded using LZW algorithm with variable code length as described in Appendix F. Okay. So we are looking at subblocks and sorry, I'm just trying to think about like how this stuff is packaged. So you have like, you know, data size data, data size data, data size data, right? And within this stuff, if you read this as like a stream of shit, the minimum code size here is outside. So it's like minimum code size, then data, data, data. And so we are pulling from this data. We might want like a subreader that automatically handles this stuff for us so that it's easier to think about the LZW stuff like externally. That's probably what I'm going to do. So we probably want like a subdata reader, and then the definition of the LZW stuff is in Appendix F. Okay. So can we do that? Let's just make the subdata reader right now. Also, can we make this packed info should be global packed info? That's going to come up later. Okay. So can we make a subdata reader? He is going to have some input reader and an interface. And all this thing is going to do is I don't know what yet. But I think it is like a stream function is how this stuff is usually implemented. I think. Because this guy's got vtable, buffer, seek, end, and the stream function is the only thing in the vtable that you have to implement. Okay. So we need to do some type shenanigans. Bang, bang, boom, boom. Okay. And what do? We like try to put some stuff into a buffer, right? So we will assert that we were looking for somewhere to write, I think. So we're looking for writable slice greedy. I guess we look at the inputs. So we say like the byte size, like block size is self. We don't have self yet, but we can get it. Self is a sub data reader, which is a field parent pointer of interface from R. So the pointer to R is like this pointer here. So we like walk back 8 bytes to find ourself. Easy peasy. And so we like look at self input and we take byte, right? Then we do something else. I think this article will help you a lot. No cheating. No cheating allowed. No, I'm not going to click your link. I'm going to read Appendix F and see what he yells at us about. So now we're like, okay, we need to read this block into this writable slice. So we say, give me at least this many bytes. And I think it's like not even greedy. I think it's literally just like writable slice. And we just copy shit into that writable slice. Right? Yeah. And then we return the block size. Easy. I guess we do need the limit to be in here. That's confusing. That is confusing. Okay, so we need to do some limit here. We need to do like next like remaining block remaining len, which we get from here. So if block remaining len is greater than 0, we try to get the next slice. So I guess it's like we try to get 1 byte at least, and we limit this with the limit, and we have like the merged limit is the block remaining length, which I think you need to do like stood IO limit limited or something, or you can do like limit min, so the minimum of the limit that they want and the limit that we want, which is the stuff remaining in the block. Okay. Then we use that to figure out where to get the slice that we can write to. And then we do self input stream. No. Read slice all. Read slice short. We're allowed to read shorter if we want, I guess. That sounds fine. Red bytes is this many. Okay. Then we return that. That's how much we read into that thing. And then we also have to advance the thing by that much. It's like something like this. Something like this. I'm not 100% sure. Good afternoon. We're going to give emotes today? Yes. Yes. And then this stuff should happen no matter what, really. And it's like if the remaining len is 0, then we do this. Right? But then there's like some like exit condition here, right? Which is that if the block remaining len is 0, we return end of stream. I think. I think it's something like that. That feels about right. That feels about right. And then now we should be able to make like a sub data reader of this thing, right? So we read the min code size. So this is a take byte, right? I don't know what that means yet, but then we have image data to read, right? And so we should be able to be like var sub data reader is sub data reader whose input is R, the data we're reading from. Great. We need to like initialize this thing probably. So he's gonna have like this. He's going to initialize himself in what way? He's gonna say block remaining length starts at 0 to trigger the first read of the first block size. Interface. I think he needs to take in a buffer here because the IO interface requires buffers. Okay. Input is R. Easy. Seek is 0. We've kind of consumed no amount of this thing, I think. And then we're looking for the vtable, which is just a little guy that says stream is stream. Easy. And I think we need buffer here as buffer. This is all in the interface. Oh, which is here. So input's up here. There we go. It's like something like this. Shouldn't the first condition be greater than 0? I don't think so. Here we're trying to like update the thing if we're already empty. I think. I'm not really sure though. We'll see. We will see. If it's wrong, it's wrong. SDR buff. Alright. SDR buff, let's give him 4K or something. Who gives a fuck? And then we should be kind of like, if we just say like SDR interface read or like discard remaining, we should see like image data len here should tell us something. And then if this is correct, then the rest of the thing should parse correctly. Should end equal 0, maybe buffer len instead? I think that it starts at 0 because we haven't like put stuff in the buffer yet. This buffer is like undefined. So I think it's like as the stream happens, it will bump end automatically. I think. But what do I know? What do I know? Expected IO limits somewhere? That's at 158. Limited. Boom. W advanced red bytes. So red bytes has to be tried. So true. Okay, and then we're stuck. Which is interesting. I don't know if you listen to anybody, but LZW, as soon as you read bits instead of bytes, you read codes. Yeah, but we're not there yet. So it's fine. It's fine. We're gonna write like an LZW reader on top of this, unless the Zig standard library already like has one. Something is wrong here, by the way. So discard remaining is supposed to call discard, which I think the default discard implementation will just call seek. And he's going to try to stream into a discarding writer. So I don't really... Maybe we're in this loop? Somebody should like hit the end of the file. Like somebody's not advancing. Oh, here we're supposed to, after we read, self block remaining len is however much we read. Oops. That might be related. Okay. Reached unreachable with LCT present. So it looks like we hit a frame from this thing that had a local color table. I think. I don't know what's printing here, but it looks like the overall structure is still parsing correctly. So that's good. That's good. If options LCT present, what are we supposed to do? Local color table. Where the fuck is this? Local color table. Boom. About color tables. Okay, here, it's here, right? So this guy is the local color table. It's just the same thing as the global color table. I think it's just identical, right? I think it's just identical. It's because the global color table was here's the size in bytes, then we take this much, and then we read this stuff. Okay, cool. So I think that we should be able to be like, read color table here. Right? So this should be able to just be like, whoop. Okay. So then down here, we're like, read color table with R, with this guy. Boom. And then we can do the same thing if the local color table is present. Right? Easy. Okay. That assert that this thing is it can go away now, and then we can assert that this is present, or there's a global or a local one. At least one of them. Okay. So this looks promising. We do see a local table here with what I believe seems to be reasonable data, right? However, we are ending up with invalid block type, and I would like to see what that is. So can we do... Because maybe it's just the end of the thing. You know what I mean? Like, maybe it's just the end of the file. Std debug print invalid block this, and let's just see if it is a sane character. Which is block type. Like, this just might be the Terminator. Yeah, so this is the semicolon, which is the end, right? I believe that's what we saw in the Wikipedia page. The trailer, which should be the last byte of the file. Yeah, hype, dude. Okay, so then we get through the whole thing, and it looks like we have parsed the overall structure, right? So that is huge for us. We have made it through the whole file without any errors, and now the next thing to do is try to actually parse the image data, which they said is LZW compress, like decompressing. Right, and they said that was defined in Appendix F. So, variable length LZW compression is a variation of Lempel-Ziv compression algorithm in which variable length codes are used to replace patterns detected in the original data. The algorithm uses a code or translation table constructed from the patterns encountered in the original data. Each new pattern is entered into the table, and its index is used to replace it in the compressed stream. The compressor takes the data from the input stream and builds a code or translation table with the patterns as it encounters them. Each new pattern is entered in the code table, and its index is added to the output stream. So there's a fucking sure. There's a code table essentially. Variable bit length table. You throw things that you see in the table, and then you can reference them later. When a pattern is encountered which has been detected since the last code table refresh, its index from the code table is put in the output stream. Easy. Thus achieving data compression. Wow. Wowza. The expander takes input from the compressed data stream and builds the code or translation table from it. As the compressed data stream is processed, codes are used to index into the code table, and the corresponding data is put on the decompressed output stream, thus achieving data decompression. This is, okay, there's a lot of words in here that I need pictures eventually, but we'll get there. Details of the algorithm are explained below. Perfect. The variable length code aspect of the algorithm is based on an initial code size, so we have the LZW code size flag at the top of the block, which specifies like Huffman doing improv. It seems kind of like that, right? That's kind of what I'm hearing. I'm hearing that as well. When the number of patterns detected by the compressor in the input stream exceeds the number of patterns encodable with the current number of bits, the number of bits per LZW code is increased by 1. There's no huffing in there. No, I understand that, but it's like, it's kind of, we have like a similar idea where you have like variable bit representation where you have like code indexing that way. It's absolutely different. Like, I'm hearing some similar concepts. I understand that the Huffman is like a different algorithm, but there is some similarities in here, like there is a code table, right? Which is just going to be true of any decompression algorithm. I like, I kind of get what he's saying. Is all I'm trying to say. Okay. Must appear before the code that terminates the LZW compressed data must appear before the block terminator. Makes sense. Okay. So the conversion of image from a series of pixel values to a transmit, I want the other way. Is there decompression? They're both algorithms. Yeah. Perfect. We got there. Establish the code size. Determine the number of bits needed to represent the actual data. So we have that because we have this. Oh, I see. So as they're building it, like they're increasing the number of bits required for each code. Is the code length constant? I was kind of thinking that like, I thought that it does say variable length here, right? So the algorithm is based on initial code size. So we start with the initial code size, and then we expand and contract as necessary as we're reading, probably. Right, so we probably read that thing first. The first byte of the compressed data stream is the value indicating the minimum number of bits required to represent the set of actual pixel values. Normally, this will be the same as the number of color bits. Because of some algorithmic constraints, however, black and white images would have one color bit would be indicated as having a code size of 2. This code size value also implies that the compression codes must start out 1 bit longer. Okay, so we might have to add 1 there. The LZW used algorithm using GIFs algorithmically matches the standard one with a couple of differences. A special clear code is defined which resets all parameters and tables to a startup state. The value of the code is 2 to the power of code size. For example, if the code size indicated it was 4, blah, 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 blah. Okay. An end of information code is defined that explicitly indicates the end of the image data stream. LZW pre-processing terminates when this code is encountered. It must be the last code output by the encoder for the image. The value of this code is clear code plus 1. Okay, sure. The first available compression code value is clear code plus 2. Okay. The output codes of the variable length, blah, blah, blah. Okay. I have to read this. The output codes of the variable length starting at code size plus 1 bits per code up to 12 bits per code. This defines a maximum code value of 4095 because that's like 12 bits or something, right? Whenever the LZW code value would exceed the current code length, the code length is increased by 1. The unpacking of these codes must then be altered to reflect the new code length. Okay. Oh, okay. Build 8-bit bytes. Because the LZW... Wait, can I just like... Is there a decompression state? No, only compression. Because the LZW compression used for GIF creates a series of variable length codes of between 3 and 12 bits each. These codes must be reformed into a series of 8-bit bytes that will be the characters actually stored or transmitted. This provides additional compression of the image. The codes are formed into a stream of bits as if they were packed right to left, then picked off 8 bits at a time. Assuming character array of 8 bits per character and using 5-bit codes to be packed, an example layout would be similar to this. Jesus Christ. Once the bytes have been created, they are grouped into blocks for output by preceding each block of 0 to 255 bytes. The character count byte. A block with 0 byte count terminates the raster data stream. Okay, Jesus Christ. Okay. Let's look up LZW. That's why I suggest you were doing it. Yeah, but I don't want to. Okay? We're going to do this my way. Okay. So, what are the differences here? We need to look at the differences again. Wait, where was the part where it said it's standard but different? Right, it's a standard algorithm with a special clear code and an information code. First available compression code value is this, and output codes are variable length. Okay. So, can we look at like a typical LZW thing? Maybe we start with like a typical LZW decoder, and then try to implement, then like make try to run that on the GIF stuff with the differences matched or something. Can we do something like LZW decoder decompressor, I guess. And I assume that like in Python I can like compress something, right? I assume there's some library I can just yoinky. Just so that I have like some test data to work with. Maybe okay. Let's look at the Nix OS package search. Can we just type LZW in here? And compress. Perfect. Perfect. Is this like a binary? Let's find out. Let's find out. This is probably a Python package, right? It's gotta be. Where are we in like the file hierarchy here? No, this is just uncompress. Wait, is this only the decompressor? Let's see what they give us. Let's see what they give us. Oopsies. We have compress. Perfect. What does this do? We have a path. Hello. What does that do? What does it do? Surely this should go somewhere, right? Oopsies. Dash C, yeah. Dash C, right tester. Oh, don't remove original. I see. Ah, there we go. There we go. Okay, we're getting somewhere. We're getting somewhere. Okay, cool. Cool. So we should now be able to try to start doing something. Okay, so we initialize the dictionary to contain all strings of length 1. Read the next encoded symbol. If the symbol is not encoded in the dictionary, go to test 7. Go to step 7. Emit the corresponding string to the output. Concatenate with the previous symbol, blah, blah, blah. Go to step 9, concatenate. Add again. Is there like a fucking example? Here we go. Encoding. So their example is looking at to be or not to be, or to be or not. To be or not to be, or to be or not. So they have an initial dictionary where they have the Terminator code at 0 and then 1 to 26 as A to Z. Is that like a standard dictionary, or is that just the dictionary that they've chosen to start with? Showing the status of the output and the dictionary at every stage. Okay. A computer renders these strings as bits. 5-bit codes are needed to give sufficient combinations, right? So there must be some pre-shared dictionary, I would think. Why do we need LZ compression again? Because the GIF data is compressed this way. Yeah, so there must be some sort of input dictionary that we agree on, right? So I assume that ncompress must be picking one. Ncompress, can I like look at it on GitHub or something instead? I don't want to download from SourceForge. It's just too fucking lazy. Compress. So there must be some initial dictionary, right? There must be. Uh hmm. This is not super trivial to look at. Okay, let's read again. So a computer renders these as strings of bits. 5-bit codes are needed to give sufficient combinations to encompass that set of 27 values. The dictionary is initialized with these 27 values. As the dictionary grows, the codes must grow in width to accommodate the additional entries. The 5-bit code gives 2 to the 5 equals 32 possible combination of bits. So when the 33rd dictionary word is created, the algorithm must switch from that point for 5-bit to 6-bit strings for all codes. Sure. Note that since the all 0 code 0 is used and labeled 0, the 33rd dictionary entry is labeled 32. What? So because we have 0 is 0, then the 33rd is 32. Oh, sure. Sure, because plus 1, because 0 is included. Previously generated output is not affected by the code width change, but once a 6-bit value is generated in the dictionary, it could conceivably be the next code emitted, so the width for the subsequent output shifts to 6 bits to accommodate that. Got it. So I don't really care that much about encoding. I want to care more about decoding. To decode an LZW compressed archive, one needs to know in advance the initial dictionary used, but additional entries can be reconstructed as they always simply are concatenations of previous entries. Right. So we need the additional. Pseudo compress has LZMA and LZMA2, different algos, but I wonder if there's anything there we can use. Yeah, it's a possible. I think that those are like relatively different, but we'll see. I'm kind of okay just ripping it myself for now. I think this is kind of like part of the fun. Okay, so we start knowing that the dictionary is 5 bits, right? So we read these 5 bits to be or not, and we're doing something like we're following this algorithm, right? Okay. So here we see something like the T, and we're like, okay, there's T question mark. We see the O, and we have 2 in here, and we're like, oh, maybe nowhere in here are we like adding a 25-bit. We're not like adding new strings to the thing yet, though, right? It looks like here is where that happens. Unless, oh, I see. We're adding as we go. We have like a 26-bit dictionary initially, or 26 element dictionary. Then element 27 is the 2 element 2, OB, BE, EO, OR. And so at each then we see we have RN now, and that we've like run out of bits. So everything is 6 bits now, right? Because we can't fit. And then eventually we're going to see some sort of repetition, right? So in here, every element under here is under the initial 26. But here, we see 27 again, because we see 2, which is the thing that we put in back here. So then, we're like, oh, now we see TO question mark. And now TOB is in the dictionary at index 36. BEO is at 37. I see. And then 2B, like this, we have like a 3-byte code now, and we pack the next thing on. I see. So back to the algorithm, it's like initialize the dictionary, read the next encoded symbol. So we have some number of bits that we know we're supposed to read, and we like look that up in the dictionary. If the symbol is not encoded in the dictionary, go to step 7. If the symbol is not encoded in the dictionary, looking again. So looking at the first thing, we see TO. Right, so we're looking for if TO is already in the dictionary, I guess. And we go, oh, we have no TO in the dictionary, so we add it, right? That's what's happening. Oh, sorry, this isn't encoding. So on decoding, we have this. Right? So that means that you must have some sort of like reverse lookup, right? You must have to have some reverse lookup to check, or you just rip the whole dictionary to check if that thing is in there already. Maybe, right? It depends on like how large the dictionary can get, right? Because I assume that we're going to see to again at some point. It has to be, right? So like you have to hash map it. I think. Okay. Add v to the dictionary and emit v to output. Great. And repeat sub 2. So otherwise, if it was encoded in the dictionary, we emit and then we concatenate the previous string emitted to the output and add that to the dictionary. Right. Right. So it's literally just you are always adding to the dictionary. Always. Right? Is there ever a case where something doesn't get a new index here? If it was already in there, I guess. Okay. Okay, so we need some sort of initial dictionary and like a bit reader, which I think the standard library I think has some sort of bit reader, if I remember correctly. I believe. Hello. There we go. Bit reader. Bit. Read. Bit. Maybe that was back in the day. Does IO Reader have some sort of like read bits? Surely not. Zig bit reader. I remember there being one before. But maybe we have to do it ourselves now. Do any Zig heads know if I'm misremembering? What's the question? Is there like a bit reader built into the standard library? I remember there being one before, but I don't see it at all in here now. I remember being able to like pull bit reader. Like I want to like have like a stream of bits that I can say, okay, pull the next 5 bits from this thing. No, but as small as possible. I remember. I'm positive that there was one in the standard library before, but it's probably just gone. I'm like pretty fucking sure. If it did, it was in studmem. All right, yeah, okay. So we just have like next byte here, and next like bits remaining, which is a U3, and we want to like we probably have like the code size here, right? Which is some size. Would be funny if you could do read bytes 1/8. Yeah. Something like this, right? And stood bit stack maybe? Is that what it is? Bit stack like it just doesn't look. I would never have guessed that that's what that was, but I guess it did say bit stack. And I just didn't look at what that meant. If that effectively a stack of U1 values implemented using yeah, it's not really what I want. But I guess you could just keep popping off this thing, which is kind of interesting, but whatever. Okay, so we probably have some sort of like read code or something. We probably have like input as a std IO reader or something. Maybe there's an analogous like bitq, which sounds like a little bit more like we want. Yeah, bitq. Yeah, I don't see it, but it's okay. It's okay. Okay, so we want something that's like we have len in bits, right? I don't know. And this is going to give us. We probably want the type that we're reading here. Maybe we assume that the code will always be U8 for now, and if that. Oh, I think U12 was the max, right? I think they said 12 was the max. If I remember correctly. And I think that we know we have code size bits here. And then is it like, how are these bits like pulled from this guy, right? So like when we pull packing order, since the codes are typically not followed by boundaries, the encoder must agree on how codes are fit into packed into bytes. The two most common are these things. In LSB first packing, the first code is aligned so that the least significant bit of the code falls on the least significant bit of the first stream byte. And if the code has more than 8 bits, the high order bits left over are aligned with the least significant bits of the next byte. Further codes are packed with LSB coding. There's some stuff in std compress, such as bit tree. I see. The higher order bits left over are aligned, blah, blah, blah. Okay. GIF files use LSB first packing order. Okay. Okay, so least significant bit first. Okay, so that means we have so if we have like code size bits, say this is like 5, right? And say we have like self bits remaining is 3, right? What do we do here? So if we're doing like LSB first packing, the least significant bit of the code falls on the least significant bit of the stream byte. So let's assume we have like the next byte here, and this is going to be masks in some way, right? So it's like, if we have let me think for a second. So there's a world where we're trying to read a 12-bit code that is packed over 3 bytes, I believe. Right? So you could have like, the most significant bit in one here, and then the least significant bit in one here, and then like 8 bytes in the middle, 8 bits in the middle. So it's not like there's a loop that can go up to 3 somewhere, probably. Maybe it's just like while remaining mask or something. I'm not really sure. So we probably have like remaining bits as a, I don't know, this, right? While remaining bits is greater than 0, we do something, right? So here we try to pull some bits out of the next byte, right? And remaining bits is subtracted by bits pulled, right? Where bits pulled is going to be the minimum of remaining bits and bits remaining. That's funny. We'll call this bits to read or something. Or I don't know how to like phrase this. Like one of these is like the amount stashed in next byte, and one of them is the amount that we're trying to read, right? So we've got like a fucking code remaining bits, maybe. We'll call it this. Okay. Bits remaining, both of these get subtracted by bits pulled, right? I think that makes sense. Code remaining bits. And so we have some output value, right? So out is a U12 that starts at 0. And then there's something here like if bits remaining is equal to 0, we pull the next byte. And this gets set to 8. Like this. Okay. Then what do we do? So now the only thing that we have to do is actually do the read, right? So it's like next byte is shifted right by bits pulled, right? And we pull out that many. So I'm not quite sure here. We need to like we need to yoink out like the last 3 bits and shift them in, right? Because it's least significant bits first. So yeah. So it's like out shift starts at 0 or something. I don't know what like the correct type here is yet. And we say like out is or equaled with next byte and mask shifted left by outshift. It's like something like this. Something like this, right? So we pull out, we mask out the last bits. Do the mask in a byte reader if you don't hate yourself. I don't know what that means. I think I am doing that, right? I have a byte reader and I have a mask that I'm generating on the fly. I think that's what I'm doing. But I don't know what you're trying to say, so maybe I'm not doing what you said, but I think I'm doing what you said. I'm doing what makes sense to me. I'm sure that we're like over instead of using bits remaining. I don't understand. What do you mean? You have to like you have some sort like you have to how to say this? Oh, you're saying instead of bits remaining, you have like mask, and you adjust the mask as time goes on. So you mask the byte, and if the mask is, you just keep shifting the mask as you're reading or something. Is probably what you're saying, right? So you have like, so then you keep peaking the next byte until the mask is 0 or something, right? So you start with a mask. You start with a mask of this. Yeah. I can see what you're saying. I see what you're saying. So this mask is a U8. That does seem nicer, right? And so you kind of just say like, as long as shifting the mask is okay, which I think it is. So then you can do something like you have bits pulled here. You have like self mask must be shifted left by bits pulled or something at somewhere. And then if mask is equal to 0, you do like a reader toss 1, right? And reset the mask. Something like this. Something like this. Looks like Zig ships an LZW sample too in lib tsan. Ah, interesting. Interesting. I'm okay with doing it myself here. But it might be nice to do it that way. Okay. So we still need to track code remaining bits, I think. Not really sure yet. And then I think this outshift is still required. This goes like this. Okay. This is still good. And so this is kind of like combined mask. We probably need that. Not sure what's going on here. We don't have bits remaining here either. I'm not really convinced this is easier, actually. We'll see. It kind of felt like it was, I had it before. Okay, but let's see. So we yeah, I'm not really convinced anymore. Like, this part is nice, but I don't know how to, like, manage it with this. There's some sort of, like, and you do, right? You do, like, self, mask, and, remaining mask? Or something? So, I'm not really convinced that this is easier anymore, because you still need to do this piece, which requires like bits remaining that you have available to you in this byte. So I'm gonna go back. I'm gonna go back to I think this is fine. I think this is fine. Okay, so let's think about this again. So we have how many bits remaining in this byte. We get the next byte and reset bits remaining. The amount of bits that we're pulling off right in this stage of the thing is however many left we have in the code, or the minimum of that and however many left are left in this byte right now. Our out gets ORed with some mask here, where the mask has to be calculated by something. Maybe we haven't calculated that yet? Mask is... what? It's like the amount of bits we're pulling. So if we, it's like 1 shifted left by this minus 1, right? Is the trick here, I think? Right, so if you're trying to pull 4 bits, you do 2 to the power of 4 is 16, minus 1 is 15, which is 4 ones. I believe that's right. I don't think it's easier on you. I think it's easier on the CPU. Oh yeah, I don't really give a fuck though. I don't give a fuck. This feels. Am I missing a step here? So we shift this right by the number of bits pulled. This guy, we have the the output updated. I think that's fine. I'm pretty unsure, but we can do a quick test. Oh, the out shift is not being updated. But that's just... I think that there's some duplicated state in here, by the way. Right? Like, we have 4 guys that are tracking bits pulled, which is, like, obviously fucking wrong. Right? But I think that that's okay for now. I think. I'm sure that there's something wrong here. We're like something that could be more efficient. But let's just do a quick little thing. So we can do input is let's say 0x12, or maybe it's easier to do it this way as binary streams. So 1 1 1 1 0 0 0 0, and then can we do 0 0 0 0 1 1 1 1, something like this, just so we have like some pattern. Am I fucking high? It's like this. Okay. R is stood IO reader fixed around the input. We can now construct our LZW decompressor as one of these guys whose input is R. Okay. We've got the code size bits. Let's say that it starts at 5, right? And let's say that the next byte is, we initialize this with 0 and bits remaining is 0, right? So the first thing that we should see is try stood testing expect equal. We are expecting this to be 1 0 0 0 0, right? Easy. Easy. Then we are expecting the remaining 3 ones. 1 1 1. And then 2 more ones, because we have the ones in the least significant over here. Then the next one should have 2 more ones and a bunch of zeros. So it should be something like this. This thing can probably fail in some way, and that means down here we need to try here. And then we're totally missing the part where we can increase the code size and stuff. But that's like kind of another step. Let's just kind of start somewhere. What is this thing fucking going on about? Oh, maybe like this? U3 cannot... okay, it's U4 then, I guess. Okay. Mask here, we want this to be... we have to do as U16 so that the full mask can be automatic, will like work here. This is like a stupid way of calculating this, but I was fine for now. I don't give a fuck. You can't make me. Outshift should be U3. Okay. Bits pulled here. Actually, I'm gonna do U4 here. I think. I'm not really sure yet. And int cast somewhere else. Wherever outshift is. Int cast here. I don't know, that feels like something will work better that way, but I don't know, I'm making shit up. Bits pulled also. I'm sure, maybe we're gonna crash here. I don't fucking know, yeah. So we're integer overflowing on outshift minus equals bits pulled. Shouldn't outshift be increasing? Okay, there we go. What are you working on? Little GIF viewer. GIF viewer. Okay, so good. We can at least read a few codes in the way that we expect. So now we need to actually start kind of iterating this stuff, right? I would love to use the ncompressed dictionary. Like, is that a thing that we can define? Like, where do we see the dictionary? Ncompress initial dictionary. Is that a thing that we can do? Look at about ncompress. All right. Maybe we just skip this part and just rip it on the GIF data directly, because I think that in the thing somewhere, it told us what the initial dictionary was in Appendix F of this thing, I think. Blah, 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 blah. Establish code size. Minimum number of bits required to represent the set of actual pixel values. So I think that we have that in the image data we pulled, right? I think. The initial code size? That sounds like it's somewhere. LZW. LZW code size, yeah. So we have that thing in there. Then so with the initial code size, it's just like sequential indexes probably, right? So we have the clear code. A special clear code is defined which resets all compression decompression parameters and tables to startup state. This code is 2 to the power of code size. For example, if the code size indicator was 4, the clear code value would be 16. So we can, right, okay. Then the end of information code is clear code plus 1. The first available compression code value is clear code plus 2. Output codes are of variable length. Oh, so like the first n bits are just like lookups into the table probably, right? So like values, if we have like 4-bit, we have values 0 to 15 are indexes into the table, then clear code, then end of stream, then the next part. That part. Yeah, that sounds right. That sounds right. Okay, so let's try to run this. So so can we, I mean, we have read code here, but we have to do the rest of the fucking decompression steps. So I think that we maybe have like a function step. I'm not sure. We might need a better name for this. Who is going to return an optional U12, probably. And this might be an enum. I'm not really sure. We'll see. Yeah. So this thing is going to either be a... No. Because this will only ever return to the caller, like, valid indexes, right? That's what we're trying to give. Okay. So we have some code. I guess... Oh my god. Can we try to decode this to be or not to be thing? We probably need to do... I think that'll be the easiest thing for us to do. So they have the... read code. So this Wikipedia example is trying to encode to be or not to be... Oh, that's also hard to fucking test. Fuck! Alright, well, maybe we just rip it. Okay. So here we are stashing the last string at each point, right? So we have our initial dictionary. So this is actually not returning a U12. This is returning like a string? Is it returning a sequence of indexes? I guess, right? So we're assuming that each input code is a U12 or like... Yeah. Each code... Wait, am I stupid? Right, I understand that the LZW code returns gives us back a sequence. So that sequence must be like a set of pixels. It has to be. So our dictionary is going to be like I don't know. It's like a auto hash map of code to sequence, right? I think that this will make my life easier to represent things this way. So const sequence is an array of U12. I don't know where this 12 is coming from in my brain. I think somewhere that they said the maximum code size is 12 bits. I think. I don't know where this 12 is coming from. So we might come back to this. So each step is going to give us a sequence, right? That sounds right to me. And I think that if I remember correctly, when we're decoding, we have to go back as well, right? So we have like reverse dictionary goes from sequence to code. Okay. Which is maybe we're kind of handling this wrong, but maybe like a flat map that you rip the whole list on every time would be easier. I'm not sure. And then we have like a last code, I think. Right? So we're like kind of doing like next we try to build like the next sequence out of this thing, right? So we start by ripping from the dictionary the code that we got. The last code that we have. Which may not exist, right? So the first element is fucked. So I'm just gonna like write this as a null initially, but I'm really not sure. I'm just kind of making that up. So we're assuming that everything that we get is in the dictionary, right? We have last sequence, I guess, is here. And we have the next sequence. Self dot code or something. Okay, next code, yeah. And if we don't have one, we back the fuck out, probably? I don't know. Okay. So then we are trying to see if the combo of these two things is in the reverse dictionary already. I think. Right? So can we use scratch allocator here? I don't know. We'll figure this out later. So we're trying to do alloc print of these two things together, but they're not necessarily strings, so it's not a print here. Is there like a concat here? I guess we allocate like the sizes together, right? So it's like next sequence. I think this is like, or else return error invalid, I guess. That way we can do this. Okay. Okay. Ooh, the dictionary is sequential, huh? So this doesn't have to be a hash map. This is an array list of sequence. Yeah. And then this is just items at this index. And I'm just gonna do like a fix me actually error instead of crash. Something like that? I'm not really sure yet. Right, because I think that the next code is always just sequential, right? We're just like, here you go. Okay, that's nicer. So then we check if this thing's in there. So self reverse dictionary get or put this thing that we just allocated. Okay. And if this thing was not in there, then we freak the fuck out, right? So we say, put that thing in there. So we duplicate this string and put it on the actual allocator that is used for our dictionary or our reverse dictionary. Right, so it's like gop value pointer is a dupe of that thing. Self alloc dupe combined or something. I don't know yet. I'm basically just going off the example and feeling it out and hoping for the best. But that seems good. Okay. Thank you for answering the color question. That is correct. That is correct. And then now what do we do? And then we also have to put it in the list, right? So it's like, oh, this is the key pointer. The value pointer is the dictionary length, and then we append to the dictionary. Yeah. Yeah, that seems kind of right. Yeah, fuck it. And then we return the sequence. Right? Is that it? Shouldn't we build the string after allocating it? It's just an empty buffer now. That's a good point. Yeah, you're right. Okay. Fuck you. So it needs to be in order. So it's combined from 0 to next sequence len. from no, it's like last sequence first, right? And then it's from last sequence len onwards is next sequence. There we go. God, you're such a fucking asshole. Why don't you fucking put the bytes where you want them? Like, jeez, man. Does that look right? And then all we need to do is build the initial dictionary. So... And then we need to handle our special cases, right? So, if next code is equal to... How can you have a code that's bigger than the current bit length? That's what I'm missing here, right? So they're talking about in here that... Oh, because it's the initial code size. So code size and initial code size are different. Right? So if we get too big, if if the value pointer is greater than or equal to 1, like 2 to the power of code size bits increases by 1, right? That's how it gets larger. Okay, and then if next code... Wait, is code difference than the value? How confusing. How confusing. But I think so. I think it's fine. So, if next code is equal to self initial code size plus 1, we need to unreachable, probably. This is like reset the decompressor is what they said, I think. Right? And then code size plus 2 was also something special. End of information. So this is return null. Okay. I mean, that's like a maybe. That's a maybe. Okay, so let's initialize this thing. And we might want like a really, really simple GIF to like test this thing so that we can like get a little smarter. But I guess we'll know pretty quick if it's correct just based off of the first couple pixels. Yeah, we can probably figure it out. Okay. So we need in here the initial code len, which they said is normally the same as the bit depth, but not always. But like for the vast majority of time. So this is showing us all of the possible things that we can use. Okay, perfect. I don't know what's going here yet. I think it has to be a U8, right? So we start by making a dictionary. I guess we need an allocator in here as well. Okay. And we're doing something like, holy shit, there's a lot of stuff in here. I just realized she's building a GIF decoder for window chat will never see. Of course. It's for me. It's for me. Stupid. Initial code size is initial code len. code size bits is initial code len. Next byte is 0 with bits remaining starts at 0. Alloc is alloc. And then dictionary. Technically, you don't have to store the dictionary for all of the initial code values because you know what they are, but I'm going to do it because it makes my life easier. And you can't stop me. Dict is an array list unmanaged of sequence. And for now, we'll go for 0 to initial code len. So fix me. Dict doesn't need 0 to initial code len. Idiot. You know? But it's easier. Bro really out here typing 2 lines of code an hour, spin up OpenClaw instance peasant. You don't have to be a fucking annoying piece of shit. I'm just gonna ban you. But maybe shut the fuck up. It's like, just so annoying. Okay. So we also need the reverse dictionary, which goes auto hash map unmanaged from sequence to code. 07 JavaScript mogs. Later. Okay, so dict append I. And by I really mean an alloc. We need to like allocate a new sequence for this thing, which is kind of funny. So this is like a thing of length 1. Sequence is this, and then we say sequence 0 is equal to I. Okay, that makes sense so far. And then this is probably cast in here. We append the sequence like this, and we also have to put it in the reverse. Put sequence I, right? It's the other way. Something like this. Okay. And then we put dictionary is dict. And reverse dictionary is reverse dict. If this works, I'm gonna be shocked. If we have the last code, it's L. And if we don't have it, it's an empty list here. And so if we see some image data, we like construct this bad boy. Right? So we say LZWD is an LZW decompressor. Initialized with an allocator that we're gonna have to figure out at some point. An initial code length of LZW min code size, then a reader of our data reader here. Okay, and let's make a scratch buffer, I guess. Which is gonna be relatively big. Let's give it like a meg. Fuck it. Fuck it. Scratch is stood heap fixed buffer allocator. We'll figure this shit out later. This will be fine for now. Then we do. Oh, we actually need 2 allocators, huh? We need one for scratch space and one for not, because the scratch space. I mean, we could also just support free, but like whatever. We could. I think we can support using the same one for both. I'm not sure. It's a little tricky because like the way we said we were going to do this is like we like build the string on the scratch allocator, then copy it over. But if we use the same scratch allocator twice, that like fucks shit up. So whatever, we'll just do this for now. Alloc buff. We'll figure this is like a big fix me. LOL. I just don't know what to do with it right now, so whatever. While LZWD step with scratch allocator, we have sequence, and we do print for sequence elem, we print the end element. Where this is the goal. Okay. And then we reset the scratch. Alright. Let's see where this goes. Surely it doesn't work. Alright. Expected one of these, found one of those. All right, try here. Okay. He's like, yo, we need 3 arguments. We need our allocator here, I guess. How can we need to do equals undefined for a buffer fixed size? Will it 0 otherwise? Just because you need to equal something. It's like one of those like just flag to yourself that it is undefined. It's not like C where it's undefined by default. You have to like opt into undefined behavior, right? Otherwise you have to initialize it. Is kind of the idea. Expected optional type found U12 at 238. Yeah, why did I do this? Okay. I don't know. Auto hash does not allow slices. Auto hash map, so we need to do something else. Consider using auto hash strat or providing your own hash function instead. Okay. What do I do here? Hello. I guess I just need to do hash map unmanaged and use the correct context. So auto context is like get auto hash function, and then he's like, dude, what is he bitching about? Consider using stood hash auto hash strat or providing your own. How the fuck do I do that? What does this return? Hello? What am I supposed to do? It's not undefined as in lack of value, but undefined as undefined behavior. It's like sometimes sometimes it's just like you use what's on the stack. Sometimes it's like we fill it with A's, type shit. Dude, I've never seen this before. I don't know how to deal with this shit. Stood hash auto hash does not allow slices as well as use instruction containing slices here. Use auto hash strat. Okay, so how do I do that? It's got to be related to this context thing, right? So we have hash and equal in here. Get auto equal function seems fine. Get auto hash function also seems like it should be fine. Consider using stood string hash map or hashing the contents of const. Alternative can use auto hash strat right here. So I guess we create our own context here. So it's like this with the context provided as like hash is stood hash auto hash strat. But this doesn't return anything. So like, what the fuck does this do? Provides hashing for any eligible type. Oh. Okay. Am I fucking stupid? What does string hash map do? He has string context, which returns hash of hash string. Oh, it's a function. Oh, okay. So we need to like maybe define our own like uh seek context or whatever, and there should be like stood hash auto hash strat who has a hasher somewhere. Uh oh, can we just do hash array? But the hash array needs a hasher. Where does the hasher come from? What is a Oh my fucking god! What is a hasher? I want. Huh. So what does it normally do in hash? I hardly know her. Thank you. What does like string hash map do? Oh, because he creates a hasher like this. So we have to create our own hasher? Maybe? And I guess like yeah. So we construct a hasher on the fly, I guess. And then oh, we can we not is there no like fucking construct a hasher for me type shit? Auto hash with hasher. Do we have does this guy have like oh my god. All right, fuck it. So we say here is the thing. Here is the hasher that we've seeded with 0. Here is the content. And then the strategy is deep recursive or something, probably. And then this is return stud meta equal AB. Jesus Christ. And this should be code. Oh my lord. Okay. Okay. And then this thing also needs max load percentage. So there's like max. There's like a stud hash map default max load percentage. Holy fucking kill me. Oh my god, we got there. Holy fuck. That is not trivial, man. That is not trivial at all. Okay. Oh, and then the reverse dictionary needs that same thing. So this is like hash map unmanaged with seek context and stood hash map default max load percentage. Holy fucking hell. Holy fuck. Okay, 265. Combined is he wants to the code type in here, I guess. Got value pointer needs to be dereferenced when we assign this thing. And then this thing needs to be int cast, I guess. Okay. And then left-hand side of shift must be, you know, this is a code or something. Expect type view 4, found U8. Another int cast or something. 279 is like, please give me your allocator. Okay. Fucking dunzo. And we are freaking out. Integers does not fit in destination type. So bits pulled is too big. Okay. Oh, so this needs to be like, if bits pulled is less than 8, we do this. Because if it is 8, we are not allowed to shift out 8 bytes from 8 bytes. Memcopy arguments alias. What's going on there? How is that possible? Are we passing the wrong allocator here? Scratch allocator, alloc allocator. So there should be no aliasing here, right? Because last sequence is from the dictionary, which should come from the... That seems like it should be impossible. Because we're using our allocator for the stuff in the dictionary. Oh. We need to we can't use the scratch version there. Okay. Index out of bounds, 28, length 11. Okay, so what are we fucking up here? So this next code is like way too fucking big. Can we print LZW size? We're gonna have to start getting like a little bit tricky with it. So we have 8 elements. Are we processing that value correctly? This is an 8-bit image? I mean, it could be. LZW code size. Yeah, it's gotta be, right? Define the number of bits needed to represent the actual data. Yeah, okay. So then it looks like we're probably pulling stuff out wrong, right? It's gotta be. It's gotta be. Can we, items, okay, so this, we start with a 8-byte dictionary, then a 9-byte, then 10, then 11. But we're getting index 28. Which means that we must, like, we have to be pulling wrong, right? So can we try to, so we are pulling 8, 8, 8, 8. Over and over and over again. This is wrong, right? This is wrong. The dictionary size should be 2 to the power of that. Because the initial code length is, it's not the number of elements here. It's how, that's like literally, like 2 to the power of that many things are in the initial dictionary. Oopsie, it's fuck. I had caps lock on and that fucks it up. Okay. So that should do something else. I don't know what yet. We'll figure that out. Okay. So now what's happening? We are getting an int cast failure at 307. What's going on there? He is trying to shift the mask in a U16 by some amount? Yeah, why? Personally, would have loved to hear you say inconceivable like in Princess Bride when you see memcopy arguments alias. Yeah, my bad. Code remaining bits or bits remaining? This should never fail, right? Because bits pulled should always be at most 8, right? Because bits remaining should be at most 8. Right? So, like, what's going on here? This is, I don't see how this could be a problem. Integer does not fit in destination type. Oh wait, this is outshift. Wait, maybe that's a bug. Yeah, what is outshift here? That makes more sense. Okay, what's going on here? So our out shift is, we're trying to shift by 8. Because mask is next byte and mask shifted left by outshift. Oh, right, because this needs to be as as code type. Okay, better. So now we're seeing a reset maybe. Wait. This might be good. So here we're seeing 0147. Then we are seeing the reset, right? So this is just self code size bits is initial code size, and then we reset the allocator or something. I guess we just do like, can we just re-init ourselves? Self is equal to init alloc initial code size and input. I guess this is that kind of should reset us, I think. I don't think it's a good way to reset us, but I think it should. And then I think we ask them to step us again. No, because we can't. That undoes that nukes the current value as well. Fuck. So it's like we need to reset the dictionary, which we'll figure out. Reverse dictionary is rebuild. Like, I guess we want to do rebuild dictionary with self dictionary and self reverse dictionary, probably. And then we probably set like last code is null again, right? Because we're resetting the decompressor state. But our next byte and bits remaining have to stay the same. And then code size also has to reset. It's probably something like that. 1, 2, 3, 4. Okay, yep. So input, this stuff stays the same. Everything else gets reset. Okay. So now we just need that like rebuild dict function, which is just this, right? Rebuild dict, which takes in alloc, initial code len, whatever this was, right? And then dict, which is a like array list unmanaged of code or something. I don't remember. And then the reverse dict is like some like reverse dict, which we should name because it's too fucking hard to type every time. Okay. We're getting there. Okay. Reverse dict is this bullshit. Okay. Yep. Then here we go. Hold on. Reverse dict. Rebuild dict here with alloc initial code len dict reverse dict. Boom. I want you in my room. Bum. Okay. Then we can do this here with just a bunch of selfs everywhere. Okay, let's try that. Close. He's like, yo, the code here, this is supposed to be a sequence, not a code. Okay. We're getting somewhere. No initial code len. What the fuck do we call it? No field name dict. Okay. Not good. So we are getting a 529 out of 519. Can we double check? So let's see what we can do here. I'm not sure yet. Let's do at least a flag here. Rebuilding dictionary. Let's just see if that's related. Okay, so I don't know. Strange. I don't know why we would get a rebuild dictionary so early in the stream, actually. Looking at what's coming out of there, like a 0147, and then he's like rebuilding immediately. That feels pretty wrong to me. What is the, like, initial len here? So the initial code size is 8. So we're seeing 0 to 256. Then we get through 3 elements. And then, like, wait, what the fuck? Next code. How is the length of that thing so long already? Right, like, shouldn't this be, like, 250 something, not 519? Right, because we start with 256 elements. Oh, fuck. Oh, we did forget 2, by the way. Because we have the 2 magic codes, right, that we know aren't allowed. So I think we have 2 that we're not supposed to have. But that's not the problem here. That's not the problem here, I don't think. It feels like the code size increase must not be being handled correctly. But I'm not sure why that would be. Yeah, that's kind of how it feels. It feels like we must be reading too many bits. Right? Or we're like tracking something wrong, like very possible. Can we next code, and then we can say like got code. Fuck. What is happening here? Okay, so 0, 1, 4, 7, 9, 11, 26, 30, and then 529 just out of fucking nowhere, right? Okay. Okay. So of bits between 3 and 12 bits each, these codes must be reformed into 8-bit bytes. It will be blah 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 blah. Oh. 8-bit bytes. The codes are formed into a stream of bits as if they were packed left to right. What the fuck? I'm a little lost on that one. But let's think for a second. So where could this have gone wrong? We are pulling some bits out of this guy. I mean, it's after the reset, right? So it seems likely that we're fucking up the reset in some way. Oh, last code is equal to null, which we already handled. Do we set last code anywhere? No. So we should probably do that, right? We do need to do that, and that might change things a little bit. Okay. I am still confused about this 500 stuff, by the way. I am still confused about that, because I would think that we should have 256 entries. Putting into dict this number. Right? So we should have 255 entries in the dictionary. That makes sense to me. Oh, we're not resetting here. Oh, shit. We should be doing this. There we go. Better. So then, this makes more sense, right? So I would expect to have 266 entries in here because we had 256, 257, 58, 59, 60, 61, 62, 63, 64 or something. But then plus the 2 indexes for the like codes that we don't support. But maybe those codes aren't initially in the dictionary. Okay, so 264 does seem right, but we still are getting code 312, right? So that is like a thing that I would expect to be possible at least, right? Because we added some stuff to the dictionary and our code size immediately increases by 1. Right, so that makes sense. What does not make sense is the fact that we're getting that data. I would also like to maybe like to sanity check if we're doing this correctly. We would have to start writing out the image, right? Because like we need to like look up in the code table, like in our color table, wherever the fuck that is, like these values and see if they look like the ones we would expect on like one of these frames, right? So if this thing's going like left to right, it seems like we should see background color a bunch of times no matter what, right? Like we should see a bunch of zeros up here, right? Because like no matter what, can we generate like a dead simple GIF to make our lives easier? Like, can we just do like a just fucking make this shit tiny, you know? Give me a 2x2. Hit me with like here we go. Give me a fucking 2x2 red, green, blue, black or something, right? Can we just save this as is GIF one of the options in here? Is it not? PNG, direct draw, EPS, dude. Am I high? Test.gif.png. I'm an idiot. I'm an idiot. What did that do? Hex dump test GIF. What did that do? That's still a PNG. Kill me. Okay, can we do GIMP? Let's do GIMP. New. 2x2. Okay, and can we give me a pencil or something? Okay, and can I put my size to 1? Perfect. And let's do a little red. Okay, well, fine. Yellow and red. Export as home. Test. GIF. Replace. And can we hex dump that thing now? That does look like a GIF, which is huge for us. Zig run, and then can we, in this thing, look at home streamer test GIF. Okay. Good news. So We do get code 03004. Okay, so this is... We might not have enough... Okay, can we do 4 colors in here? I don't know. Okay. Okay, here we go. Here we go. Okay, so... Interesting. Can we look at what this guy has in him? So the image data is here, right? So zeros, a couple twos, and down here we get some... So we're freaking out immediately, right? Can we look at the code line? Code len is this. This should be small as fuck, right? Should be. Because we have so few little shit in here. Code len is 2, okay? Perfect. So we start with 2, we read 2 bits, we get a 0, we read 2 bits again, and we should get a 0 again, right? Because like the beginning of the data stream here is like zeros all the way through here, right? So we should be getting zeros. But we are not. We are getting code 7 instead. So how the fuck are we managing that? Right? Like, am I crazy that like read code 2? Oh fuck, this stuff, this won't compile anymore. God damn it. But we should be seeing like, is it automatically compressing the image? I mean, that's kind of what we're trying to get out of this thing, right? Okay. So code len 2, GIMP, I mean. But like, I mean, it looks like we see something in there, right? Like this stuff has to be LZW compressed data. Oh shit, no wait, am I fucking stupid? Is the header taking up some of this? Wait, I might be fucking stupid. I might be fucking stupid. Hold on. Right. So we are supposed to see image separator followed by 1, 2, 3, 4, 5, 6, 7, 8, 9 bytes. So it's the top left, top right, 5, 6, width, height, 9. Okay, so this is the data we're seeing actually. 02, 03. So he reads the first 2 bits, 0. Great. Then he reads the next 2 bits and he should see 0 again, right? Because this is 4 bits, 4 bits. Right? So can we take a look at this guy? So when we say read code, let's try to see what's going on here. So remaining bits. And let's print out like out and out shift as well. Out and out shift. And let's flag that we're doing a new read here as well. Code time. Code time. Okay. Whoa, am I fucking high? Okay, so we have code time. Remaining bits 2, out 0, shift 2. Next. Oh my god, am I shifting the wrong way? Am I shifting the wrong way? Okay, can we go back? Least significant bits first. So we are seeing data starts here, right? So we read the first 2 bits, we get a 0. We read the next 2 bits, we get 0 again. And then we should see the 3rd bit should come from this nibble, which should also be 0, by the way. So the fact that we're getting 7 is insane. Can we look at bits pulled? Okay, stood debug print. Next byte. Are we not shifting next byte down? We are doing this. Okay. So let's look at the hex value of next byte at this thing. There's no way that's right. There's no way, right? Because it should be one of these. Unless I'm fucking high. Pulling next byte 5C. Oh, wait, because the first byte of this thing is its length? Wait, so that actually might be right. Okay. So this is top left, top right, width, height, pack, length of the stream, which is 2. So this is the length of the image data or something? But then what is this stuff down here? Yeah, that's a little confusing. Hold on, looking at it again. Oh, wait, okay. Sorry. So one of these things is the code size. So this is the code size. No, this is the code size. Aha, code size here. Code size is 2. Makes sense. Then we have 3 bytes of data. 1, 2, 3. So the first byte of the data is 5C. Wait, okay, this is making sense. So we're chilling there. So the first byte is 5C, which lines up with everything that we've seen so far. Then we should see that we pull the first byte. Can we like format this as binary? I think it's like this. How do you format as binary? Like this? Here we go. So we should pull the first 2 bits. And we should not commit anything to the stream yet, right? Because on the first pull, there's nothing to commit. So we fucked up on the last code thing. We're doing something wrong there. This should be like this. If last code, all of this stuff only happens if there's a last code. And then this stuff is LC here. Yes. Yes. And then next sequence comes out here. Okay. Oh, that's so much better. That is so much better. Okay, we actually get to end of stream here, which I think is good. So here we get code 0, 1, 1, 2. Oh, wait, hold on. I feel like now we're going for too long, right? We have too many prints here. So can we just turn most of these bad boys off for a second? Okay. So what is the size of this GIF? Right, because this should be a 2x2 pix, like a really fucking small boy, right? Yeah, this is a 2x2 image, which, by the way, Gwenview can't even show. So the fact that we're getting 1, 2, 3, 4, 5, 6, 7 bytes here seems wrong, right? But it could be that our like end of thing is not working correctly. Because we're expecting this, right? This is kind of weird too. Oh, I see. Oh no, wait, I see. So this is the LZW length. This is the first block, 3 bytes, then a second block of 0, then the terminator. Okay, so this is the only data in here. 5C0405 is what we should be seeing. So if we come back and we say the next byte log, we should be seeing it pull 3 of them here. 5C0405. So that is correct, right? What is not correct is us seeing so many pixels here, I would assume. Okay, so we're getting way closer, way closer. Can we print got code here as well? I want to understand what we're saying here. So we get code 0, we get code 3, we get code 1. Okay. Can we show this with the code one as well? Pulling next byte. Okay. Interesting. So what is this stuff supposed to represent? Maybe we should look at that again. Image data. Okay. It says a sequence of subblocks of size at most size 255 each, containing an index into the active color table for each pixel in the image. Pixel indices are in order of left to right from top to bottom. Each index must be within the range of the size of the active color table, starting with n at 0. Okay. So this should only give us 4 bytes of data. Some of the bytes would be the special control bytes, right? Not just image data. It still feels like it's too much. Like, yeah, I agree. Yeah, I agree. I feel like we're so much closer now, though. Okay, so we are I think this might be off. This might be initial code size plus 0 and initial code size plus 1. Okay. Not quite. Can we double check this again? So the special values are Appendix F. Appendix F, Appendix F. Special values. This value is 2 to the power of code size. Yeah, so this would... Oh, wait, hold on. Oops. This is like this. 2 to the power of initial code size plus 1. Okay, let's try this now. That makes more sense. Oh, fuck. Oh, fuck. Oh, fuck. Oh, fuck. Int cast here and here. Kill me, kill me, kill me, kill me, kill me. I'm sure that these are invalid in some ways, but whatever. Oh! Wait. Is this right now? 0, 3, 2. Rebuilding dictionary and Dunzo. All right. Oh, but when we're Dunzo, we still need to return something? No, we're Dunzo. The code has no sequence associated with him. Okay. So we're closer now. So we should be seeing yellow first, right? Top left should be yellow. So our first code being 0 seems wrong, right? Like, if we're doing top left to bottom right, then we should start with index 0, 1, 2. Right? So can we look at the Python of bin 0x5c again? I feel like we're going the wrong way. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, I feel like we're going the wrong way. No? Because if we're expecting this first, then that would be the top 2 bits, not the bottom 2 bits, right? Right, like I would expect here, if we're going top bits to bottom bits, it's index. No, wait, that would be index 1. Wait, no, that doesn't make sense either. That doesn't make sense either. This is yellow down here, right? 0, 1, 2, 3. 0, 1, 2, 3. Huh. Yeah, there's something in here that I can't quite place it. Can we hex stump this again? So it's these 3 bytes are the compression stream, which should just be 4 indexes, right? So why is there so many 4 indexes plus a control code to stop? Right? So shouldn't shouldn't there be enough in like 1 byte? Almost? Is it possible that we're not supposed to be putting everything in the output stream? Okay. If the symbol is not encoded in the dictionary, emit V to output. Concatenate the previous string emitted to the output with the first symbol of W. Add this to the dictionary. Go to step 9. Emit the corresponding string. Wait, hold on. Can we look at the steps again? So in their decoding example, they see T 2 B or not. So that's all fine. Then these things get put in the dictionary as we go. So there's something emitted for every code, right? For every code they emit something. So that makes sense. And I'm pretty sure that they're only ever just looking at the last thing and appending the current thing. I mean, that all makes sense. This Dunzo is just appearing way too fucking early. Okay, so we see 0. Okay. This 5C. Bin 5C. So if we're reading bottom to top with a bit size of 2 initially, we should read this. And on the first thing we read, we should not increase the dictionary size. Right? Because there's nothing to increase it with yet. Right? Let's look at the steps again up here. If the symbol is not encoded in the dictionary, go to step 7. But here the symbol is encoded in the dictionary. Concatenate the previous string emitted to the output with the first symbol of W. But we're not like, okay, so we don't emit anything yet. Then we get, oh, we put 2 in the dictionary, so that's the first thing that pushes us over the edge. Unless our code length starts as 3, because there are codes that are valid that are like 2 to the power of blank. Would that make more sense? So if our code length starts as 3, we would get 7 off rip, which would be an instant reset, which would seem stupid. But then we would get a 3. Does the 3 make sense? It might. It might. Right, because the 3 was yellow. So there's a chance. There's a chance that our initial code size needs to be immediately 1 larger, because our dictionary needs the special flags in there or something. You know what I mean? It could be. It could be. There's no way, but like maybe. I mean, that looks more correct. That looks correct, right? That looks correct, because we see our yellow here, index 0, 1, 2, 3. Then we see index 1, which is the blue. Then index 2, which is the green. Then index 0 is the black. So that seems kinda right. It's kind of fucking crazy that you just immediately increase the initial code size by 1. But I mean, maybe. Can we try parsing the other GIF as well? The one that we have like, what was it? Test. What is it? It's some emote. Oh, I mean, we get through everything and nothing crashes. I mean, that's really fucking promising. That's really promising. Can we, for each image, output it as a ppm right now? I think that's possible. I think that's possible. So can we create a ppm writer here? Do we have... Ooh, okay. Stood fs current working directory open file test ppm create file. And we have ppm file, I guess, and we have our ppm w buff is a 4K buffer of undefined. We have ppm w is a ppm file writer. This is tried. Ppm w buff, boom, and then we print immediately p6 the size of the image. So it's like, I think width, height, and the max pixel value. So 255, and then I think a new line. I can't quite remember. And so here we're like, hit me with the size. So we should have this somewhere, right? Where is our image width and height? Image width, image height. Okay. Then we should, for each of these elements, we should be able to look into the table. So can we write the table down somewhere? So when we read color table, this should be this should return some sort of table of RGB values. Okay. And then here, we should have an allocator here. And then can we do like color table something like goofy of Tootsie remember me? Ah, we fuck it, we ball. Fuck it, we ball. So here we create some RGB things like this. Okay. And then we do ret at I over 3 is like color table I plus 0. I don't know, man. G and B. We go like this. And then we have like ret at I over 3 is equal to R is R, G is G, and B is B. Let's fucking go, baby. And then we return ret. He is mad about R being both a reader and a color value. And instead of fixing the names, we'll just do this. When we read the color table, we have var global color table is some sort of RGB slice is empty. And then we reassign it here. Okay. We need an allocator here, so we're just gonna move this up, and we'll deal with the fucking fallout later. Okay. And then now we are going to index into the global color table every time we see this. So we're gonna say ppmw. We're gonna say like color is the global color table at elem, and we're going to do ppmw interface right byte color R followed by GB. And then we are going to somewhere flush this thing. Okay. And then I think we're just gonna crash. All right. Read color table. Okay. We need to try when we write these bytes because it might fail. And I mean, that looks pretty bad. That does not look good. Can we try it with the test? Can we go back? Home streamer test GIF. Let's try this one again. Oh my god. GIMP. How can we open this in a way that Okay, so at the very least, this one is working correctly. Can we try again with this? Yeah, okay. So we have successfully read something. How do I say this? We have successfully read our shitty one. We have not successfully read this emote that we got from Twitch. So that's not good. I think that we should also assert here that the remaining like the 0 or something. Which, I mean, okay, here, so remaining data. This is right. Oh, wait, does it have a local color table? It might. Hold on. I think that this thing did have a local color table. So we should do var color table is global color table. And then if the local color table is present, we look at that instead. Does that look a little better? That's closer to looking like something. Fuck. Still not great though. Can we double check here? Got local color table. Oh, and then also, can we, if true, return here? I want the first frame. There's too many pulling. Next byte, can we, got code. All right, let's get this thing out of here. Okay. So this thing is not using the local color table, which I think is not really good, because that means we're doing something wrong. That means that we're doing something wrong. Can we... Not ideal. Not ideal. It's weird. Hold on. It's weird that it is parsing this correctly, right? Like, we're getting through all of the data. Can we count how many things we've read, actually? Var written bytes. And we'll just say, like, written bytes is increased by sequence len every time. Right, and we should see, like, parsed bytes is this many. Parsed bytes is 1156. So if we look at 28 by 28, 784? Oh. Well, that's not good. Right, that's not good, because we should be seeing a 28 by 28 thing. So that's confusing in many ways, right? Because that means that our like LZW decompressor is working, and it's exiting at the point that the block is over. And all of the indexes that we're turning are valid indexes in the stream, but, or like in the color table. All of those things are true, yet somehow we've put out too many bytes. That's confusing. That is quite confusing. Very strange. I wonder if it's the reset. Maybe on reset we're not supposed to have, like, there's something weird happening. Because we do see a rebuilding dictionary in there. I don't know what to do with that. P6 is RGB, not RGBA, right? I think so. But I think that, like, the fact that it works when we use our own tiny GIF is at least some confidence that we're writing out the PPM correctly, right? When we do home streamer test GIF, right? When we do this. And then, fuck. Right, so that's promising. Can we maybe make a bigger, like, can we do something like this? New, can we just paste from our clipboard, like new from clipboard or something? Maybe we do this and then paste and then image crop, maybe? Crop to content. There we go. And then export as test GIF or test2. Hello? Oh, I need to actually do the export, huh? Oops, we're ooming somewhere on... Yeah, that makes sense. Because we're not, like, fucking freaking ever. Fuck. Okay, let's make it smaller. Because we're not using our allocators correctly at all. Or we could just do this instead, actually. Try stood heap cage allocator alloc just fucking go crazy. What if we just give it more? The easiest fix. The easiest fix. So now he's mad. We should just... Shh. Shh. Oh my god, we actually are still ooming. Wait, is it really the scratch allocator is running out? Why? Because shouldn't the scratch allocator... It's getting reset every step. So it actually... I'm surprised that this is getting into trouble. Actually quite surprised. But what if we ignore that too? Alright. Well, does it at least look like it resembles something sane? No. Okay. Okay, so our super simple test case worked. But anything more complicated than this did not. So I'm sure that we're just doing something fucking brain dead. But I mean, it's exciting to see at least this. Look at us go. Look at us parsing a GIF. We're kind of over time is the thing. So I would love to continue and fix this, but I think that finding out the problem there is going to have to wait for another day. Because, I mean, we're an hour over how much we usually want to go. So thanks for watching, guys. If you like what you saw, we stream most days. We aim for 12:30 4 o'clock Pacific time. It is 5 now, so if you're watching live anywhere from, what is it, like 4.5 hours ago, and an hour ago is when you should expect to see us live. We're working on this Twitch chat client, which should have a few things that will make it to the YouTube. But the things that don't make it to the YouTube are archived on Patreon, Twitch, and on YouTube members segments. If you want access to those VODs, you pay, you help the stream continue, everyone's happy, bing, bang, boom. But yeah, otherwise, no worries. I think that's all I got to plug. YouTube, peace out, and Twitch will find someone to raid.